right, so we're doing number 1. You guys are writing down your variables. Tell me what you're writing down. Margaret, what's the first thing you're writing down for number 1? Okay, Robbie, what's next? Okay. So it's going from 25 to 40, so how do you do temperature change? Which way? Right, so T final minus T initial. So T final is the 40, T initial is the 25. It's going up, so it's going to be a positive temperature change, which means it's absorbing heat. So what is that, 15, right? Okay. Lindsay, what's next? Lindsay. So we got the mass, we got the temperature change. What's the next variable given to us? We're looking at problem set 17, number 1. Okay, so what variable is that? Q, thank you. Okay, so Q is 124.2 joules of heat. And then the question is, what's the specific heat capacity, or what's the specific heat? Just don't get mixed up between heat and specific heat. Specific heat is usually called specific heat capacity, which has a C with it. But when it doesn't, like in a problem, a lot of times they cut it down from specific heat capacity to just specific heat. That's why you miss out the capacity part of it. But once you see these variables, you should know which equation applies. EJ, which equation applies here? MCAT, right? MC delta T, MCAT, right? So Q equals MCAT, and then from here, you know me, I'm not a fan of plugging variables in until the very end. That way we don't mess up units and questions. So, Miles, how am I going to solve for C? That's what I mean. We could plug them in at the end. Can you rearrange this first for me so I can just solve for C? So, after you get to MCAT, I want to solve for C. So how do I isolate C is what my real question is.
Divide by
and okay, so divide by M and delta T. So then they cancel on this side, giving us C by itself. So then Chem, we're going to plug in. So Q over M delta T. What's my Q? Joules, right? And then mass. Thank you. All right, so you guys should have the ability to find C. You guys have a calculator in hand. How much you got?
0.46 joules per gram.
Joules per gram degree Celsius. That's the answer on the bottom. Is that exactly what you got whenever you calculated?
Yeah.
Okay, I didn't know if it was pre-rounded. Okay, so this is our post-rounding. So here's our C value. And then it says, look at the values listed in your textbook, identify the unknown metal. You guys actually have reference tables right in front of you, at least maybe close by. Look at the upper left-hand corner of the reference table. There's a little chart on the front side of it. There's a chart with specific heat capacities of metals. There should be one pseudo close to you. Who has a specific heat capacity close to 0.46? Who? Which metal, Nick?
Well, this is iron.
So what's iron's specific heat capacity?
0.449.
0.449 joules per gram degree C. Is there anything closer? All right, that sounds good to me. I'm going to go with iron. So this is likely iron then. And you could identify that based on these characteristics that are pre-established in a table like this. All right, so the Q equals MCAT one's probably very easy for you guys. Let's get down to one that looks like a calorimetry problem where you have multiple variables involved. Actually, there's not that one, actually. 3 is actually, it says calorimeter, but it's not a true calorimetry problem when you're having to set T equal to Q. It actually gives you enough to solve for just that one. So look on problem set 17 and tell me where you see one where we have to do MCAT equals MCAT. Okay, I don't see one. Do you guys see one? Oh no, how about 9? No, actually, let's scooch back to the other side. So the lecture problem notes, you guys have calorimetry. We did number 1 on the board in the lecture problem video. How about 2, 3, 4, and 5? Looking at those, which one can I set up and solve for you guys? 2? I said 2. Which one? 4. Let's do 2 or 4 right now then, okay? Let's start with 2. And this is an important fact to write down. And you saw this in the video at one point in time, but 4.18 joules per gram degree C. That's the specific heat capacity of water. Well, the specific heat capacity of water is a lot of times based on recognizing that water is a very inherent characteristic. We use water as a comparison for many, many things. Specifically, the calories in the back of your nutrition labels are based on water. And so there's a value that you should recognize, 1 calorie, right, little c calorie, but these two things are equivalent. So if you're ever having to convert between joules and calories, you should have 4.18 joules is equal to 1 calorie. And that's going to be relevant in question 2. So whenever you're setting up problems like these, I always identify which is the system and which is the surrounding based off the reading, and then also organize the data table accordingly. So you have a metal and you have water, and you're given lots of information about each of them. Generally, M, C, and delta T about each of them with one variable missing. So if you set up your data table, kind of like this, as we read, we can fill it in. And so this just helps with organization. So 2, a block of rhenium metal, and it says C is 0.0329 calories per gram degree C. So 0.0329 calories per gram degree C is heated to 88.2 degrees Celsius and then dropped in. So I hear that initial temperature, right? So whenever I do T temperature change, I'm going to do T final minus T initial. All right, so with that information, I know that the 88 is the backside, it's the initial, 88.2 degrees Celsius. So I'm just setting it up in my equation like this. It dropped into 100 grams of water, so the mass of water is 100 grams. The final temperature of the water and the metal is 32.4. So if we're, oh sorry, the water initially, I missed that point. The water initially is 26.4 degrees Celsius. And then it says the final temperature of the water in the middle is 32.4. So they're both final temperatures is 32.4. So we're going to subtract those, and this is again 32.4. What's it called when they end at the same temperature? Thermal equilibrium, right? So if the metal and the water are not stopping at the same temperature, something's wrong. They will always stop at the same temperature. Right, so we have our T final and our T final. And then what's the mass of the rhenium metal? So question is mass of the metal here. What's the only thing we, okay, well, we can calculate the delta T's, but what's the only variable we don't have on the board that we actually do know? So we do know the specific heat of water is 4.18 joules per gram degree C, but I just told you that joules and calories were related through this conversion. So then what's the calorie version of that for water? Say again? Just 1, right? It's 1 calorie per gram degree C. Okay, so we have MC delta T. Let's go ahead and calculate this. What are these two variables, guys? You guys probably maybe already did this. Negative 55.8 for the metal, and what for water? 6 degrees Celsius. Okay, from our system and surroundings perspective, what this looks like, and this is what your drawing may include whenever you have your, in your foldable, a calorimeter, a really cheap version of a calorimeter, are just 2 styrofoam cups stacked together. That's it. It's just a really good insulator, right? Styrofoam. Who's ever used styrofoam cups to keep their drinks really hot or really cold? Okay, now we've got Yeti cups, but it's basically just a double-walled cylinder with air between it, which styrofoam cup is just a bunch of air embedded inside of this plasticky kind of stuff. So this is a calorimeter. So what's happening is they're dropping this little piece of metal that's really hot, 88.2 degrees Celsius. They're dropping it into water. So I'm helping you with your pictures if you're drawing with me, okay? So this is your water at 26.4 degrees Celsius. this is like smoking hot metal, right? So as this occurs, this transition of heat is going to occur, which will influence the temperature change as well. So who's losing heat? Who's losing energy? The metal, right? So the metal is going to be losing energy because it's hot and it's going to deliver some energy to the water. The water is going to gain energy. And so how is this impacting our calculations? It's just basically we need to know who's going to have a negative sign. So when we set this up, the energy of the metal, Q metal, is going to be equal to the Q of the water. The value is exactly the same. It's just one is losing and one is gaining. So the metal is going to lose energy, so we put a negative sign here. The metal, the water is going to gain energy, so we put a positive sign here. Now that's going to allow us to kind of appropriately plug our variables in. So at this point, we have 6 variables, right? I don't have Q or Q at all, but I have the things that are equivalent to Q, which are MCAT. MC delta T is equal to Q. So I'm basically substituting in for the metal here, the variables that give me information about the metal. So this Q is negative, because the negative's out here, MC delta T as it relates to the metal. This Q over here is essentially MC delta T as it relates to the water. So the M's are different, the C's are different, and the delta T's are different because they're regarding different system and surrounding variables here. Have I lost anybody yet? Give me like a smile if you're in a good place. Just like a little like goofy smile. All right, I have some frowns. Turn those frowns upside down. Okay, so what a variable am I solving for here? What's my one thing I don't have? Massive what?
Metal.
Massive metal, right. Okay, so I'm solving for this guy right here. I need to get the M by itself. So what am I going to do mathematically now? Divide by?
Heat and the change in temperature.
And the negative, right?
And heat.
So the negative cat, okay, negative C delta T of the metal, divide by, same thing, right, negative C delta T of the metal, and I like to put in there to reference talking about the metal here. So that gets rid of the negative, that gets rid of the C, that gets rid of the delta T. M of the metal is left all by itself, which is what we mathematically need. So M of the metal is equal to MC delta T for the water divided by C delta T for the metal. And so from here on, we just plug. And so that's why our data chart being very organized is pretty dang important here. So what's our variable, what's our mass right here? Yeah. Yes. Sorry, there's an imaginary negative there. I didn't bring it with me. What's the mass of the water? 100 grams. Okay. C of water? 1 calorie per gram degree C. Temperature change of water? Say again? 6 degrees Celsius divided by negative what was it, 0.0329 calories per gram degree C. And the C of the, the delta T of the metal was negative 55 point, what was it? 8. Sorry, my data table's like hidden up there. So at this point in time, you're able to calculate, but you also need to double check your units cancel as needed, and they do. Our grams here and grams here. I can actually, here, I'll cancel this gram. Here, I'll do you guys a favor. It looks a little easier if you cancel the things that look very similar in a question, like our specific heat capacities first. So if you see that your specific heat capacities can cancel, I think you should do that first. Calories, calories, grams, grams, C value, C value. And so, Celsius, Celsius. So this is the complicated variable. I like to go ahead and cancel this first. And you see your degrees Celsius and degrees Celsius can cancel, leaving you with grams here on top, which makes sense for the mass. Yes, ma'am.
Sorry. Why did you do no?
Because that's our metal, that's our water's temperature change, because it went from 26.4 to 32.4, and the difference there is 6. It's very specific to the water, and then the other one was for the metal.
26.4 final.
No, 26.4 was the initial, so it's T final. They both end at 32.4. That's at thermal equilibrium, and then you minus the temperature initials for each of them separately. All right, let me leave you to your wits for a second. So I've done a general one, and then a specific, a calorimetry one. Can you guys work in groups for about maybe 10 minutes or so on concept 17 and or the lecture notes? And go through a couple more of those, and I'm going to do one with a heat curve. Okay? So know that you're going to get concept 17 done eventually. That's how you work together.
So it's all the heat purposes.
Basically, what we did there.
No, it's just a once a month. Yeah. I'm confident when I saw it. So it's well, you know oh, it's just
Oh wait, the water's supposed to be what is it? So you have that. But you're putting it on. Can you just tell me your codes for
it's just but it's still
yeah. Really? So wait, now you're trying to find Q, right? Wait, right?
I know that like the data gives us 6%. I got 1.4.
Yeah.
Negative.
Yeah, I didn't know. I got one. No, it's not. It's supposed to be like.
Yeah, I think this is probably. You know, I think she's good. Yeah. But I'm trying to. I don't get it. What's number 4? She got the number right. She's got a negative. I got the number right.
I
You
didn't
you said
know.
46.3. It's a positive. How come she doesn't give us an answer? Other 4.
What's 4?
It's just that. No, it shouldn't be that. Wait, vaporization's
Melting is excellent.
At the end, once you get Q of water, you can say Q of water equals negative Q of pebble. And so it's just show that last statement and then flip the sign. And the answer is right. The answer is 150 or 146 joules. But with reference to the pebble, it's losing so many things. It's just identifying systems and surroundings.
Okay, so vaporization. What's the
So it's taking in.
I'm just double checking, man. Come on.
I said that it's weekly. Oh, actually, I think it'll send it because I remember fusions would take it.
What is fusion?
And the Thermo. Well, I don't know. It's a
Oh my god, this is terrible.
trust me, look. Is fusion end of Thermo? Because it's like taking this.
Guys, on number 3 on the problem set, just look at this one point, this one factoid up here. It says water and it says pebble, right? They don't give us any information about the pebble, but they say pebble is hot, pebble gives energy to water, water's temperature goes up. So that kind of gives us the reference point of if the pebble is hot, it's losing energy to the water is not as hot, so it's getting energy, so it's gaining energy. So once you use your information to calculate Q of water, you already know the Q of the pebble. It's just opposite in sign because from the perspective of being lost, it has to have a negative sign. So when you're freaking out about the negative, don't freak out. Think about system and surroundings, put it in perspective, and then you're good to go. And that's the values a teeny bit different due to the sig figs that are there. Yeah. Can I ask us to pause? Can I do another question from the heat of phase change section, which is I'm doing number 4 on the lecture notes from the 3rd section. I'll either do number 4 or I'll do number 5. You guys tell me. Do 4 or 5. Can I get a 4 in the air or a 5 in the air? 4. Okay, I'm doing 4. I'm doing these because look, at the end of this, you'll have all the lecture notes done. You'll have all the problem set done, so you'll turn all this in together. Okay, so if you don't have something complete on your paper, do make sure that you're finishing up with me as we go. So this one's going to take a couple minutes, and it's also going to take some space. So have your reference table in front of you. I'm going to walk you through what you have on your test as well here. So, guys, it says how much heat, how much heat, which we know is Q, is required to change 52.9 grams of ice at negative 15 degrees Celsius to steam at 230 degrees Celsius. You'll notice that we have a lot of things going on, right? So we have ice, and it gets to steam. So we have phase changes going on. How many phase changes are occurring? 2, so we're fusing or we're melting, and then we're evaporating. And so that's going to be 2 phase changes, which are 2 of the equations that don't have delta T in them. And then we also have a large temperature change that's occurring, but it's undergoing 3 different states of matter as it does that, right? Go ahead and look on your reference table on the upper left-hand side, and look where it says heat of fusion, heat of vaporization. It also says specific heat of ice, specific heat of liquid, and specific heat of steam. Say steam. Right? You see those values for water? Yes, these are the thermodynamic constants. So we're going to use those constants here now. Just have those kind of close by so you can see them as we go. And while we're doing this, what you should be probably visualizing is what kind of graphic is in your head right here that might relate to this information. The stairs, right? So a heat curve. So we did one similar to this, but a pretty short one at that. So go ahead and draw yourself a heat curve. This is the pinnacle of thermochemistry, okay? This is a pretty inclusive question. So we have temperature change on one side, heat added, or time on the x-axis. And we're starting where? What temperature? What temperature? Negative 15. We're at negative 15 degrees Celsius. This is ice, right? So this is solid. You should be labeling this as we go so that we can kind of think about what's going to occur at each of these steps. Okay, then we're going to phase change. So ice is going to phase change to liquid. Well, this is called heat of fusion, right? And I'll show you 2 different ways to do heat of fusion. The one that you did in your notes, and then I'll show you another one using constants on your paper. Okay, and then we have liquid that has now formed. So once the solid is melted, it's turned liquid, and liquid's going to increase in temperature to a point, and then it's going to eventually have to what? Vaporize, right? So evaporate here, and that's heat of vaporization. That's a constant you guys wrote down. And then the last step is going to get us all the way to our vapor phase or a gaseous phase. But what temperature do we peak at? 230, right? Okay, now there are some temperatures in between that actually matter here. So ice doesn't just keep on being ice, right? It's going to eventually change to liquid, but at what temperature? At what temperature? Right, so it's going to freeze, aka fuse, it's going to melt or fuse or freeze at the same temperature. Just depends on which way you're going, either from solid to liquid or liquid to solid. So this first section is going to have a temperature change of what? What's this first section's temperature change? 15. So I'm going to put delta T equals 15. That's going to remind me that for later. The second section doesn't have a temperature change, right? So what equation would be relevant here? Not the Q equals MCAT, right? Because we can't have a delta T of 0, because then that would mean Q is 0, and there's not a chance that heat exchange during heat of fusion is 0. Yes? So that's the constant. What's the equation? Q is equal to mole times change in H value?
Yeah.
Okay, so heat of fusion, for example. So did you guys write this equation down in your notes? Yes? Okay. You could either use moles and delta H of fusion, the constant I gave you in your notes, which was 6.01 kilojoules per mole, or you can use Q is equal to just simply mass, which the mass is given to us, right? So we don't have to convert to moles, times the H fuzz, I think is how it's referred to on your reference table. Do you see that in your reference table where it says heat of fusion? It doesn't have a delta with it though. It just says HF in your thermodynamic constants up here. Do you see that one? What's the number that's given to you with the HF there? 334 what? Joules per gram. So they've given us another chance to use grams if we need to, which might be helpful for us. So we're going to use this shortly. Okay. So we know the temperature change equation is relevant here. Then the non-temperature change equation, which is heat of phase change. And then we have another temperature change, which is what here? From liquid up to, when does liquid turn to vapor? For water. At 100, right? So label your next little caret point over here to be 100 degrees Celsius. So what's my temperature change here in the liquid phase? Say again? 100, which is my T final, minus 0, which is my T initial. So this temperature change is 100 degrees Celsius. So 100 minus 0. And then what's my next thing that's happening? We are phase changing again. So which equation goes with phase change? Not Q equals MCAT because there's no delta T. Right. Times the change in heat that's required for this phase change would be not fusion but vaporization. You can use either the top one or the bottom one, but we would change fusion to vaporization. And then the last step would be, let's go ahead and heat that gas from its 100 degrees Celsius point all the way up to what? To 230, right? So what's my temperature change here? 130 degrees, right? So you're going from 230 minus 100, so it's 130 there. How many steps did I take to get from start to finish? How many steps did I take? 1, 2, 3, 4, 5. Yes, there are 5 steps there. That means there are 5 Qs that make this whole process happen. And so cumulatively, we would just take those 5 Qs, add them together, and that would be our total heat from -15 to 230 in terms of melting ice and causing temperature changes and all. So we have 5 Qs here, okay? You ready? Do you think you can plug all the variables into those 5 Qs? Or do you want me to walk through the whole process? I'll walk through the whole process. All right, so Q1, which is this first section here, equals MC delta T, right? We have a mass, we have a C value. Oh, but the C value is not 4.18. What is it for ice? What is it for solid ice? Look at your reference table. So was it 52.9, by the way? So the mass is, this is MC delta T, okay? The mass was 52.9 grams. It was 2.05. Is that for ice? Okay. Give me a thumbs up that everybody actually sees what we're looking at on the reference table. Okay, cool. Just making sure I'm not imagining that you're looking at it. Okay. What's my temperature change for section 1? I labeled it too. 15 degrees Celsius. Okay. All right, so someone over here calculate that for me. We're going to get back to that one in a second. So that MC delta T is what we use for when there's a temperature change occurring. What we got, Jillian? Oh, not grams, joules. Okay. So we have a little, 1,600-ish joules that's required to just get ice from -15 to 0. That's it. Then we have to undergo this heat of fusion. I'm gonna let you guys use either one of these, but for the simplicity of this problem, I'm not gonna take our grams to moles right now. You can use this one because this is how I showed you in your notes. But I'm also gonna let you use your reference table to see that the mass times delta times H of fusion might be a little easier because it eliminates that one step of converting from mass to moles. So again, now our Q2 is a heated phase change. There's no temperature change at all. We're going to do mass times H of fusion. So what's the mass in this question? Same old, right? It's what it's been the whole time. 52.9 grams of water. What's my heat of fusion? I think Rishi told me that earlier. Okay, so 334 joules per gram. That's given to you in your reference table. That allows our grams and grams to cancel. It keeps us in joules, which is great because I don't want to have to convert to kilojoules if I don't have to at the end. So somebody calculate that for me real fast. Anybody? Give me some help here because this moving really slow makes you sleepy, and then I'm just going to stop doing problems if I can't get some participation, please. Thank you, Nick. 17.
Oh, 1766.
So 17,668.6 joules, something like that. Great. Okay, so that's our Q2. So the first one, the second one. Now we're in Q3, which is going to be, I'm actually going to do it over here. Q3 is our next step, which is our, what'd you get?
Is that 52?
52.9 times 334.
18,000.
Did anybody else get 18,000? Double check. 52.9. Do I need to do calculations with you guys?
Oh,
Okay. Alright, I trust you guys are calculating okay. So now that's section 3. Section 3 is our liquid phase now. So we're going to have same mass. Now our normal C value, which is our liquid water, which is what again? 4.18, and we have a temperature change here of 100. So we're going to do our third Q using, with respect to liquid water, MC delta T. So mass of 52.9 grams, C value of 4.18 joules per gram degree C, which is given to us in our reference table. We also use that one very, very, very often. And our temperature changes was what again for the third section? 100 degrees Celsius. So grams cancel, degrees Celsius cancel, and joules are remaining. Margaret, can you calculate that for me? Okay, that sounds good. All right, so we've got Q, Q, Q. We're only to the liquid phase. What temperature are we at right now on our curve, our graph? We're at liquid, the top of liquid, which is 100, right? So we're at the vaporization stage now. What equation would I use for this flat section here? So mass times, or moles times the vaporization, not the fusion one, right? The vaporization one. And here we go. So Q4 is, I'm just going to do the mass one, that way we don't have to take time to convert to moles right now. So looking at the heat of vaporization, which is on your reference table, it's different than the one I gave you in your notes. The one I gave you in your notes was with respect to moles. So still 52.9 grams. What's the value in your reference table? All right, Darcy, calculate that for me. Sorry, start off again. One more time. Thanks. I don't know if my hearing's going or you guys are really quiet, but somebody's got to speak up. Okay. Last step. So the Q4 is the energy takes to vaporize water from liquid to gas. And then, Caroline, what's my last one? What was my last equation? So we've gone from here to here through the liquid. Now we're vaporized. What equation goes with this one? MCAT or a phase change equation? Not in this one, right? This one's actually got a temperature change associated with it. So if it has a temperature change but has a slope, it has to be the one with the delta T in it. So what equation has delta T in it? MCAT, right? And so our delta T here is 130 because that's how much energy, or that's the temperature change to get to the peak. So now we're going to do MCAT for the last time. But our mass, mass is the same. That's not a but. What's the C value for in steam? Is it 2.02? Okay, thank you. So you're looking not like at the wall, you're looking at the reference table, you should see 2.02 joules per gram degree C associated with steam. Temperature change was what, 130? I hope. Okay, so grams cancel, Celsius cancels, joules remain. And can I get one person to shout that one out for me? 890. That's right. Okay, so all of that information, that one sentence gave us all of that information. It's just learning how to see when it talks about phase changes that you have to use the mass times vaporization or moles times the delta H of vaporization. Lindsay? So that's what I told you guys. I just wanted to show you in your reference table, they gave you a constant. That might be useful. So this up here in green, these are two equivalent equations to be used for phase changes. So a good question, on your phase change section of your foldable, you wrote down moles times delta H of fusion. And I told you delta H of fusion was blah, 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 kilojoules per mole. So if I told you moles, the one that would be expected would be the moles times the kilojoules per mole constant. However, if you have your reference table, what you'll notice is there is no kilojoules per mole given to you in your reference table. Instead, they dumb it down, and they don't make you convert to moles. They give it to you in grams. And so that's why I said mass times the H fuzz with H vaporization as it correlates with your reference table. Maybe something else you want to know that is possible. It's the same exact thing. It's just the variables are there just in two different ways of writing it. So this could be another equation to write on your foldable if you wish. Just mass times H of fusion. All right, so at this point, I'm still not done with my question. What do I have to do? Add all those Q's up. That's your answer for 4. So I've left them with some cliffhangers here, meaning the decimals, so that you can get good sig figs at the end. But all of these Q's should be added up. And it's really nice right now because they're all in joules. So you're able to move on there. Go ahead and continue on problem set while you wait on me to answer a couple more questions. I'm going to be around. If you have questions, let us raise your hand.
Wait, so you got
1,000. Oh wait, no, those are only 4.
Go ahead, guys, and continue. You have your problem set, you have your lecture notes. We were gonna do a last day, but I don't think we have time, so I'm gonna kind of let you guys catch up on practice.
What is this video?
It says November 5th.
Today is not November, but yeah.
It says something. Okay. It says something.
Today's November.
Caroline, I'm scrolling up.
Are you right there?
She said smart.
I wasn't.
It's kind of it's kind of like that. I'll just do it. There's no more word.
Oh, see, that's very good English. My parents can read it. I'm just going to go for it. I like to read that one. And those are English.
Oh, sorry, for me.
Wait, we didn't finish 4. So you graduate here,
It's just together. That's how much said. I was reading
so it's Excel?
Wait, it is? Okay. Yeah, I'm gonna ask you. No.
Okay, so what's okay, yeah, I just said endocrine.
I just checked all of these stuff.
It's Excel.
I checked those. I'm trying to help friends.
I'm just gonna sit here. Okay, how much do you need? Okay, so how would you go about
Yeah, you find
Yes.
Yes.
Does it have high energy, solid energy, okay, like this last one we did. This one?
Yeah, that's
Okay.
a lot of.
That's because when you read it, you have to think about baby steps what's happening. The ice doesn't just give these names. It takes a lot of steps and energy to get there. So in a question that ever goes from a state to another state, graph it and make sure that you know which steps are being applied. Because this is the extreme. This is like include everything. Went from a very negative number to a very positive number. 3 state changes in between, or 2 state changes in between. 3 states matter in between. I did the extreme for you. But like when you look at questions. How much? That means solid water at 0 degrees Celsius versus liquid water at 12. Isn't that great? That gives you what solids oh, and you can see now somebody a hot water Fusion, thank you. So we are just going to use the information from fusion. Okay, what equation oh, I have maybe we're
It's just catch-up day, so if you got some stuff to finish from Friday, like in terms of foldable, I'll throw some information for foldable back on board. But I'm trying to give you guys a chance to clarify, so I didn't see for any much more.
You have to sleep. No, don't do it. I'm bad at filming. Just do it. No, I'm just telling you how to do it. No, yeah, you're right. And then you cut it into four halves. Alright, so you gotta start with what do you guys? Oh, so you did
Okay, I see.
Heat of fusion of the water. Did you write anything in it? Did you write anything in it? Yes, you were supposed to finish. Yes. At least he has writing on it. That's a story. That's how I call us thinking about this. Is it a cube? Is it a what's that called? It's the formula. Is it a capital 85? I can be here. That's real. Because you get a 3.5 credit for just taking the AP class. You don't have to take it. How do you get all of that? I'm going to multimedia. You know, like everyone thought this was yes, Wait, who's not that long? No, you how much heat is it? So would that be I'll do it.
What?
This is so which one is it? It's a mole. It's a mole times violation. It's actually not that bad. Okay. We have to use that mole triangle H fusion. Yes.
Either one of those will work, depending if you have moles or grams.
Okay, guys, I'm just gonna grab your attention real fast. On the video that you watched with the introduction to the foldable, you should have something with information on it. It's a piece of paper. You've got colorful piece of paper. You could have flaps, you could not. Are you good on understanding what's going on in your flaps? The only one we've not done is this last one. So you have like Q equals MCAT. You're gonna have a drawing that would relate to like why would you utilize that equation. You've got your definitions of your variables with their units. Thumbs up on that one. The other one is the calorimetry one, which is Q equals Q, or system equals surroundings. One is positive, one is negative. You can define that. What kind of image might you draw inside of the calorimetry example?
I don't know, the little cube inside the beaker.
So like a plug, or the calorimeter, which is like a coffee cup, and you can draw the heat exchange within it, a thermometer in it might even be good, because that's how we measure. And then the Q is equal to moles times delta H diffusion, or your replacement for that, mass times H diffusion. What could you draw for phase change? So a heat curve, right? Which has phase changes on it. You could draw something melting. You could draw something related to phase changes, right? And then the last one we haven't done yet, but I might actually finish that with you guys today in about 10 minutes, okay? So I'm giving you guys some time to talk with me, talk seriously, stay on class.
Which one? Let's try to finish this. You have to use the, see the things you circle in the green? The things you circle in the green? Yeah. Use the bottom and see where it says mass times Q. Wait, what did that mean?
Okay, so the x-axis is the reaction progress.
And the y-axis is the energy.
Okay, I'm going to put PE for potential energy. So PE means potential energy, or just put E for energy. So, and then reaction progress. Well, guys, if we have a reaction, don't we have reactants and products, right? All reactions have reactants and products. So put R on the beginning for reactants and P at the end for products. R at the beginning for reactants, P at the end for products. So what you should realize now, and this is going in your foldable, or either on the back of your foldable if you don't have enough room, these are graphs that give us information about how much heat is lost or gained within a reaction. So this gives us information about heat loss or gain in a reaction. And so a reaction can be written out on a graph like this, or literally written like a reaction is always written for us, which is in a balanced chemical equation. So if I have a reactant and it's yielding a product, this is generally, this is just a general format for that. Reactant yields a product. I can do the same thing over here. reactants yields products, but I just don't care what the reactants and products are right now. However, there is a difference between these, and we're going to now include that as energy. Is energy lost or gained in an endothermic reaction? Gained, right? And you can tell the reactants gain energy as they form products because the energy is higher. So maybe write down here, energy is gained. Now, if energy is gained, does that mean energy is being added to the reaction or taken out of the reaction? Energy is added to the reaction. So here's where we're going to add energy. Energy is added to the reaction. I'm just going to put add kilojoules, something like that, so you understand that this is energy, this is heat. So I'm adding it on the reactant side. So wherever you wrote your reactants for the endothermic reaction, put add energy or add kJ for kilojoules or add J for joules, something like that. Because what you should realize is energy is gained, I'm going to say as a reactant. Because it should be showing that it's being added to the reaction. And the only way you can add to a reaction is if you add it in the reactant side of things. So what we call this now is a thermochemical equation. And actually, we'll show you an example on your on the note sheet you have. We'll get there in just a second. So I could have like ammonia plus 100 kilojoules yields some sort of product. And so this energy right here that's added in the reactants is actually represented on the graph as the energy it takes to get to the products, but it's the difference in energy from these two beginning and end sections. So this energy is actually this energy right here. It's the difference between the reactants and products. And so I can draw that there. And let's say I just said this was 100 kilojoules, something like that. That 100 kilojoules will be what this is right here. It's the energy difference between the reactants and the products. And so now we're not only talking about what are the chemicals, but it's also the energy component to a reaction as well. So for an exothermic reaction, what can you imagine? I guess let's go back up. For an exothermic reaction, is energy gained or lost? Energy is lost. Okay, so energy is lost. So if energy is lost, do you think it's being used as a reactant or produced as a product and then let it evaporate out? Not evaporate, be transitioned out. So look at how these should oppose each other. Should the energy be a reactant or should the energy be a product? It should be a product. Energy is going to be produced and it's going to exit. So I'm going to add kJ, or energy, just the units for that, as a product. So energy is a product, and that's just going to go away. It's not going to be used anymore. It's just going by, right? It's going to transition out of the equation or out of the reaction. So that loss of energy as a product is represented by the difference in energy that's associated with this graph. So let's say I put this as 50 kilojoules of energy is produced, or 50 kilojoules of energy is lost. That difference is going to be here as well, from where the reactants start to where the products end. That's going to be 50 kilojoules. So this energy, we can just basically now include it in a reaction, and that's it. So this is one way to write a thermochemical equation, but these are just like fake letters, right? We don't have true reactions, true products in front of us. Another way to write it is look on your notes, which is on the back side. It says thermochemical equations, use textbook for energy formation values. Looks on the back side of your lecture notes you've been working from. I'm only going to do like one or two of these right now. I'll do the rest of these a little bit later. Here we go. Here we go. Okay. So this is what you see right on your lecture notes, right? Okay. So energy can either be included in the reaction, or the energy component can be listed out to the side of the reaction like this. So you should just recognize that either one will work. So in this first example here, calcium oxide plus water yields calcium hydroxide. That's the reaction. But for the thermochemistry part of it, they put the delta H, which means the heat associated with that. They stick it out to the side of the reaction. And so what they're saying is it's negative, right? Well, that negative delta H, does that tell you? That tells you one thing. It's either endothermic or exothermic. Which one is it? Exothermic. So you should recognize a negative means that this is an exothermic reaction. So does the graph look like this? Or does the graph look like this? this one, right? So it's going to lose how much energy? That much energy, so 65.2 kilojoules. So these equations can actually be related back to those graphs. So now this is an actual chemical reaction. This is actually a chemical reaction. These are not chemical reactions. Why are they not chemical reactions? These right here. Okay, so there's no chemical rearrangement, right? There's no new chemicals formed. There's no evidences of chemical changes. These are all just physical changes, right? What's this first physical change? Going into solution, right? The apparent disappearance. It's not melting. It's actually disappearing because it's solids going into liquid or into aqueous phase. And so the delta H of solution, SLN solution, it says it releases, so the negative value there, releases 445.1 kilojoules as that process occurs. That's really hot. That gets really hot when you make sodium hydroxide solution. Ammonia, when it melts, you tell me, this is where you're adding the sign, okay? If it melts, is it taking in energy to do that, or is it releasing energy when it does that? Okay, yeah, because you go from your solid to your liquid phase, which means it gains energy, so it's going to be a positive there. And then water, I don't know if the little dash is there, water gas to water liquid. It's going from crazy gas state to kind of calmer liquid state. Endo or exo. So it's got a, why exo, Pranny? Right, it has to release its pent-up energy from its gaseous phase, so it can calm down enough to be a liquid here. All right, so this is kind of like the overview of how does an equation look when you write your energy component. But like I said, you could also say, like, for example, water gas yields to water liquid, and then say this amount of energy is produced with that process. Which you should remember writing. You should remember doing this when you did your individual notes on entropy and enthalpy and disorder. Do you remember an equation similar to this, the energy embedded? And you identified if it was endo or exo based on the location of the energy as a product or a reactant? Maybe? Okay. I'll just do one of these for you guys right now, and then we'll hit the rest of these later. So these variables here, like for example this one, you guys recognize that because you write that down in your notes. You write down the water's heat of fusion was like 40-ish kilojoules, what? Kilojoules per mole, right? So this is how much energy is released per 1 mole of water. I can use that as conversion factor. So on number, well, I'll do it now for the appropriate one, for the decomposition of 0.25 moles of sodium bicarbonate. Let's go back up to the sodium bicarbonate one. Which of these has sodium bicarbonate in it? 1 through 5 up here? 2. Okay, so this one has sodium bicarbonate. So this is an interesting one because it's usually per 1 mole, right? Well, if your equation says differently, you have to use what your equation says. And so this particular example says this much energy, so 129 kilojoules of energy is required for every single one of these reactants and products in accordance with how many moles of them are in the equation. So it's just like a mole ratio. You have 2 sodium bicarbonates, they require 129 kilojoules. But for the production of 1 mole of carbon dioxide, it requires the same amount of energy to be produced. But everything is based on what's spoken of. So this particular example says 0.25 moles of sodium bicarbonate. So write 0.25 moles of sodium bicarbonate. This amount of energy, 129 kilojoules, is utilized for every how many sodium bicarbonates? Look at the coefficient. Sodium bicarbonate has a 2 with it. So think of it like a mole ratio. It does depend on how much you have of it. So this amount of energy is required to be consumed or used for decomposition of 2 moles of sodium bicarbonate. So we'll hit up some more of these, but this is basically like a thermochemistry mole ratio where we use energy instead of just moles. And so this would be 0.25 times 129 divided by 2, and that would be our final answer for how much energy, how much heat is lost or gained. We'll have to decide if it's lost or gained here. Chloe, you got me?
About 16.12.
16.12. 0.25, and that would be moles cancel, right? Would be kilojoules. And so, guys, you tell me if this process is utilizing energy, so you can see that's a positive value. Is that energy that's gained or lost? Positive value, gained or lost? Gained, so I'm going to leave it as a positive value there. And so I would round that to like 16.1, or 16 actually, because of the 266 here. So I think there might be one of those on your problem set, but not very many. So I'm going to do some more of these. We'll finish up these guys later. Okay, so take the last couple minutes to talk in your groups, your table groups, about what you're doing. Your problem set 17 is not due tomorrow, but since we have some time class, I expect you to get to be done. So I'm going to ask you to hold on to your lectures, your web tests, and talk to something so I can get some more questions out of you. I'm not worried about it until I feel like you're good enough in terms of like keep all your summertime together for now before I take it. I'm going to have you time to press down. All that we're doing right here. Are we just going to